Hello and welcome back to my channel. In many design guides, you will see the recommendation: choose your crossover frequency to be around one-tenth of the switching frequency. That works reasonably well in analog control, but in a digital control buck converter, things are different. We have sampling, we have computational delay, we have zero order hold effects. So the question is, how do we choose crossover frequency correctly in a digital system? In this video, I will give you practical design rules you can directly apply. The crossover frequency is not just an arbitrary number. It determines how fast your converter reacts, how much phase margin you have, how sensitive your loop is to noise, how robust the system is under different operating conditions. In digital control, crossover frequency is constrained by the switching frequency, the sampling frequency, and most importantly, digital delay. In classical analog control design, a common guideline is: choose the crossover frequency around one-tenth of the switching frequency. Why? Because you want sufficient separation between the switching ripple, the LC double pole, and the control bandwidth. In analog system, this often works well, but digital control introduces additional phase lag that this rule does not consider. In a digital control system, the output voltage is sampled once per switching period. The controller then computes the new duty cycle. However, that duty cycle is only applied in the next switching cycle. This creates an effective delay of approximately one sampling period. This delay introduces phase lag, and the higher your crossover frequency, the larger the phase loss caused by this delay. So digital delay directly limits how high you can push your crossover, and this limitation is often underestimated in digital designs. In practical digital power designs, I recommend a more conservative starting point. Instead of aiming for one-tenth of the switching frequency, I typically start around 1/20th. Why? Because digital delay reduces phase margin much faster than many designers expect. Starting conservatively gives you higher robustness, better tolerance to parameter variation, less sensitivity to timing jitter, and you can always increase bandwidth later, but recovering from instability is more painful. Let's take a practical example. Assume we have a digitally controlled buck converter operating at 200 kHz switching frequency. We sample once per switching period, so the sampling frequency is also 200 kHz. That means the sampling period is 5 microseconds. In most digital implementations, the effective delay is approximately one sampling period. So we can assume a digital delay of about 5 microseconds. Now let's compare two crossover frequency choices. A conservative choice would be 1/20th of the switching frequency. That gives us a crossover of 10 kHz. A more aggressive choice would be 1/10, which results in 20 kHz crossover. Now remember, phase loss increases linearly with frequency. So when we double crossover frequency from 10 kHz to 20 kHz, the phase loss roughly doubles. Even though 20 kHz might look attractive because of a faster transient response, digital delay significantly reduces phase margin. That is why I prefer starting conservatively at 1/20th of the switching frequency, especially in industrial applications where robustness is more important than pushing bandwidth. Engineers often try to push bandwidth as high as possible, but in digital control, higher bandwidth increases sensitivity to delay. A slightly lower crossover frequency often produces cleaner transient response, less ringing, and better behavior across temperature and input voltage variations. So, design is not about maximum bandwidth, it is about stable and predictable performance across operating conditions. For boost converters, there is an additional limitation: the right half plane zero. The crossover frequency must be well below the right half plane zero frequency. Otherwise, the system becomes unstable regardless of phase margin adjustments. This is another example that crossover selection is topology dependent. In my designs, I typically target around 70 degrees phase margin in the continuous time model. Why so high? because I expect 10 to 30 degrees of phase loss once digital delay and discretization are included. This ensures that the final implemented system still has more than 50 degrees of phase margin. That ensures implementation robustness. And in industrial applications, robustness is more important than maximum bandwidth. In this video, we discussed how to choose crossover frequency in a digitally controlled buck converter and why a conservative approach is often more robust. If you would like to see a complete design example starting from the small signal model through compensator design, including digital delay modeling and full C2000 implementation, I covered that step by step in my voltage mode control course. The link is available in the description. Thank you for watching and I will see you in the next video.